The Dark Age of Memory Corruption Mitigations in the Spectre Area by Andrea Mambretti. Enjoy.
Thank you. Today I'm gonna talk to you about our work on how we managed to bypass memory corruption mitigation, so using speculative execution. Before going into the details of the talk, I'm gonna present a little bit myself. I'm Andrea Mambretti. I'm a system security researcher in IBM Research in Zurich. And before that, I was working as a PhD student in Northeastern University. And my area of interest are low-level system security and hardware security, kind of the bridge between the two. So before starting, I would like to thank you for being here. I know I'm sitting in between dinner and then karaoke and stuff. So thanks for being here. You will see a lot of assembly, and it's kind of heavy for 6:30 p.m., but we'll see. Before going really into the beef of the talk, I need to introduce some concepts to be sure we are all in the same page, right? So the first one is transient execution. As you may know, most modern CPUs employ speculative execution and many others optimizations as a way to speed up performances. And whenever they employ one of these optimizations, basically they generate what we call transient instructions, which are pretty much as any other instructions. They cross the pipeline, right, of the microarchitecture. But these instructions are based on a guess that the CPU have taken in some situation. And the idea is that based on this guess, the guess can be correct or wrong. If the guess is correct, then this instruction is gonna retire, right? And what this means is that the side effects of this instruction are actually gonna be architecturally visible. So our program that is running at the architectural level is gonna see the side effects of this microarchitecture, the micro instructions. However, sometimes the CPU makes mistakes, and so then these instructions are gonna be squashed, and nothing will be seen at the architectural level. So our program running at the architectural level doesn't even know that these instructions are actually have been generated, right? At least this was we were thinking before 2018. After 2018, early 2018, with the discovery of Spectre and Meltdown, we now know that this rolling back operation is actually not complete. So some side effects that these instructions have during the crossing of the pipeline actually stays in the microarchitecture. And these are actually going to be visible if we employ something like a side channel. So what are the steps for a transient execution attack? So how we can leverage these? What do we need? We definitely need transient instructions going to the microarchitecture. We need to have these instructions to access a secret, right? And by doing so, these instructions will leave some side effects in the microarchitecture that is a function of the secret that we just read. And then finally, we need a side channel that will allow an attacker to go and poke the microarchitecture and basically retrieve the secret. So the threat model for this type of attacks is always a local attacker, right? And we have a victim program that is holding some secret data that we want to leak. And the attacker program and the victim program, they generally share the CPU, right? Because the microarchitecture in which they run on. So the attacker is generally local. When I say attacker program, I mean it's a very loosey term, because in reality we mean attacker code, because the attacker code can work as a different in a different program, different process, in a different thread, or even sometimes in the same address space, right? So let's have a look now at the first version of Spectre, just to have an idea of what is the context that we are working on. So the Spectre version 1, which was found in 2018, exploit a piece of code such as this one. And Spectre v1 is also known as bounce check bypass. As you can see here, we have a bounce check on an array. And if we pass the bounds check, then we can actually, execute the following double array access. So let's concretize this example a little bit. Let's assume that our array 1 is actually 8 cells in size, and we are running this code with x equal to 15. And we assume that x is actually attacker controlled. And then we assume that there is also a second array that is shared, and this is going to be used for like basically as a final side channel. When we execute this instruction, right, and we assume that this size of array is actually not into the cache, this is a specific type of situation. So when we execute this, the modern CPU, what they will do, they will say, okay, I will need to ask main memory for this variable, right? And this is a very expensive operation. So since it doesn't want to lose any cycles, what it's going to do is going to try to guess based on the history of this same instruction. If the CPU has seen the same virtual address many, many times, it's going to have a history of if the branch at this point is going to be taken or not. And so if we assume that this code has been executed with X inbound previously, then the CPU will believe that X is inbound also this time. And so what's going to happen is that the CPU will start to speculatively execute the inner part of this if, because it's based on the guess that X is inbound. So we are going to be able to do the first array access, right? And this array access, we know that is out of bound because we are executing this piece of code with X equal to 15, but our array is actually much smaller than that. So what we are going to do is like we are going to retrieve a byte somewhere in memory, right? And then if we are lucky enough, the speculative execution window is large enough, the CPU might actually execute also the second array access. And the second array access is going to be sent to the main memory. And we assume that the second array is actually not cached. So this, the execution of this instruction will never terminate because it's not cached. So the request is only sent to the memory subsystem, but then the CPU will figure out that the first guess was wrong. And so it's going to roll back all the instructions that we executed so far. None of these will be committed at the architectural level. However, since the request has been sent to the memory subsystem, the memory is actually, this request is actually served by the memory subsystem, which has no knowledge that those instructions that requested this operation are actually rolled back. And so now we have in our cache, like one cell from the second array, right? And so the attacker now, what he needs to do to retrieve this signal, he needs to go and poke basically each and every one of the cells of this array, and only one of them is going to be accessed faster than the others, because now it's already into the cache, right? So by just timing each and every one of the access of this array, we know which cell has been loaded, and given the way we have retrieved the position of this cell is going to give us the character, the byte that we actually accessed in the first array. So basically, we know that the 0x63 cell was the faster one, and then we know that 0x63 is actually the byte that we retrieved. Now, if we repeat this process across the board, so we repeat this, let's say, attack with X, with various like assignments, then we can basically scan all memory, okay? So that's why it's actually a pretty powerful attack. I'm going to present you very quickly like a second variant of Spectre, which is called Spectre version 101, or speculative buffer overflow. The piece of code that has been exploited is pretty much similar, so we have a bounds check, but instead of having the double array access, what we have here is actually a store, right? And this is on the right-hand side, it's the status of the stack of our program, right? And now if we execute this, the same piece of code in the same conditions, so the size of the array 1 is not cached, what is going to happen here is that we are going to be able to execute this instruction. And now on our stack, if we select X, craft X in the correct way, we are going to be able to overwrite, for instance, like the saved return address on the stack, right? And if we assume that the speculative execution window is large enough, we might be able to speculatively also execute this return. And what this means is that we will be able to sort of use the value that we now overwrote on the stack as our landing point for the return. So it's where actually we're going to return. We are not going to return to the correct function anymore. And this particular operation, this particular variant of Spectre gives us a very powerful primitive called speculative control flow hijack, right? We'll see throughout the talk the use of this a little bit better. So in our work, when we started this work, we wanted to see, we wanted to try to get this primitive, right? Because without this primitive, these type of attacks are kind of limited. So Spectre version 1, for instance, the first attack I presented, there is not actually a POC in the wild in the real world settings. The only POC that was presented when Spectre was published was actually for Spectre version 2. And there they used one of the, this double array access, but they couldn't find one in the Linux kernel because it's a pattern that is not really common. And so what they did was actually they introduced this gadget using the eBPF. So they used the JIT compiler inside the kernel to place one of these gadgets, right? But that is possible in the kernel, but not everywhere. So we want to get this control flow hijack if you want to exploit normal applications. So there are two ways to get to this speculative control flow hijack. One is by using microarchitectural components. For instance, we can take in the microarchitecture the RSB, which is the return stack buffer. That is this microarchitectural component that is used to predict the return, where we are going to return whenever we use a return instruction, whenever the value on the stack is not readily available. So the CPU keeps an image of the value that is on the stack, just to be sure that if that value is not readily available, the CPU can still guess where it needs to return without waiting. So this is, again, speculative execution. Or the BTB, which is the branch target buffer. These other microarchitectural components is instead used to guess where we are going to jump or we're going to call for indirect call, indirect jumps, whenever the target is actually not readily available into the cache. We didn't consider these attacks because there was already previous work that worked on this. So what we did look was actually the architecturally visible elements. So by architecturally visible elements, I mean we can gain speculative control flow hijack by overwriting register and memory locations. And we can do this overwrite in a speculative manner or an architectural manner, so concretely. And we can, of course, overwrite either a backward or a forward edge. Now, we call this subfamily spear attacks. And the first one that, so the speculative overwrite of a backward edge is actually the variant that I showed you just before. It's like this variant Spectre 101. However, there are other variants that nobody really considered. So we took that and we just looked into the possibility of exploiting those situations. Of course, now if you take as an example architectural override of a backward edge, that's a very fancy way to say buffer overflow, pretty much, because we are architecturally, concretely overwriting a backwards edge, right? That's what happens in the buffer overflow that we all know, right? So the idea here is that if you have that kind of primitive and it's not mitigated, then you just do a buffer overflow. Why bother with speculative execution? So in our case, we always consider this primitive to be present, but also mitigated by memory corruption mitigations that we are aware. For instance, stack symmetry protector in this case. So in the presence of that mitigation, we know that that attack vector is not usable anymore, right? As it is. And so what we did was actually investigate, can we use Spectre to actually bypass the mitigation and still perform some sort of attack using this attack vector. And so I will show you that, yeah, it's possible. So the first steps in this work that we did was actually using a tool called a Speculator that we built to reverse engineer the microarchitecture. Speculator is a tool based on performance counters and gave us the ability to really look into the corner cases of the CPU, leveraging a specific performance counter that we call markers. So the idea here is that with Speculator, we are able to write a very small snippet of code, corner cases that we want to analyze. And by placing a selective number of instructions in a specific location, we can have those instructions to be marked by the performance counters. We select these instructions because these are the only instructions that are seen by the performance counters, even though this instruction will not retire. Most of the performance counters, of course, are meant for performance. So the assumption there is that most of the instructions that are tracked, they are required to retire to be tracked by the performance monitor system. With these instructions instead, and these performance counters we selected, there is no data requirement, which means that if we place them in a place where we expect speculative execution to go after we gain a control flow hijack, we can actually verify that speculative execution went there without having them to retire. And this is a requirement because whenever we perform a speculative execution attack, the attack instructions will never retire, will never be seen at the architectural level, right? So what we did with Speculator, we wrote a small test like this one. This test is for the architectural override over the backward edge, which is pretty much like the buffer overflow, right? So here, what we do is we make a copy of the return value on the stack. Here we basically, we perform the architectural override. So we take the value on the stack of the return address on the stack, and we overwrite it with our target location, so where we want to jump. And then we basically just put an integrity check, emulating pretty much like the stack canary, right? And this integrity check, we know for sure that is gonna go always to the routine myExit, because the two values that are compared is one, the return value on the stack and its copy, but we know that one of the two has changed because we overwritten it, right? So this check will always fail. However, what we do here is we place this CL flash operation, which clear the value, one of the two values from the cache. So it just evicts this value from the cache. And this, what it does, this operation is basically triggering speculative execution during the comparison. Because now one of the two elements in the comparison is not readily available anymore, so the CPU will not wait and will start to guess. Now, if we assume that the integrity check has been performed before with no corruption, then what is going to happen is that we might be able to get to this return and then get a control flow transfer. And these are the results that we found. So we wrote 4 different tests, of course, for each and one of the cases I was showing you before. And this, in particular, is the results for this snippet I show you. The control flow transfer pretty much happens 100% of the time, which means that this is actually an attack vector that we can use for performing the attack, right? Of course, this is a snippet of code that we wrote. It's very artificial. There is, nothing of this is actually in the, usable in the real world because CL flash operation, for instance, is not really used in common code, right? So what we did next, of course, after we verified that this attack vector is present, was actually to try to bring it, to build like a locally arbitrary memory read in the real world. And these are the steps that we found are necessary to actually perform this type of attacks in the real world. First of all, we need to find the eviction set. In each and every one of these attacks, we need to make sure that whenever this is, for instance, an integrity check or a comparison for the bound check, one of the two values of the comparison should not be into the cache because we want to trigger speculative execution and we want to make sure that the speculative execution window is as long as we can. Because if the speculation window is short, then we cannot really execute many instructions, and so maybe we are not going to be able to get to access the secret, right? And also we want to, sometimes the speculative execution is still employed even if we don't do this, but the speculative execution window is going to be maybe 1 or 2 instructions, pretty much useless. And then we also, of course, initialize the side channel, which means that we need to create a place where this signal is going to be stored, and generally is a shared array in this type of, we need to find a shared array between the attacker and the victim. And if we use, for instance, ROB, that was one of the contribution of our work, you need to also initialize the ROB gadgets you're planning to use. Then, of course, the attacker needs to send a crafted input that is going to trigger the vulnerability in the victim code. For instance, a buffer overflow or the corruption of a function pointer, which is what we call the spear code. And once we trigger that vulnerability, if we do everything correctly, we expect speculative execution to start, and we expect to gain basically control flow hijack. And we expect to be able to run our code in a ROB chain that can be 1 or more gadgets. And this ROB chain, in this particular instance, so we are not exploiting the application. We are not getting a shell, because everything that we do is actually done during a speculative execution. And as I was mentioning before, anything that is done during speculative execution is rolled back by the CPU. So we are not going to get a root on the machine. What we are going to get is actually a leakage of information, right? A leakage primitive that allows us to do an arbitrary memory read, okay? So the ROB gadgets that we are going to use are going to be aimed towards getting the side channel sending information. And what it's left from the attacker point of view is to retrieve this side channel using his own side channel receive gadget. There is one important step that I skipped so far, which is this eviction loop, right? This eviction loop is a loop that allows us to keep that information I was mentioning before that is used for the comparison to be outside of the cache. And this is necessary to make sure that we maximize the speculation window. Without this without this step working correctly, the attack is basically not working. So we build a real-world end-to-end attack using against the stack smashing protector. And the code that we exploit was similar to this. So the spear code was similar to this. We have a generic buffer overflow, right? So we have a buffer, and then we have a mem copy. The attacker controls the source and the source size. So we assume that the attacker is able to overflow the buffer and gain control of the return value on the stack. But then we know also that this is not exploitable anymore because there is a stack canary check, right? So the application is compiled with the stack canary. And so then basically the application architecturally will always abort, unless we have, of course, other primitives that we can use to bypass this. If we don't have a primitive to read the canary, then we cannot really do anything about it. But the idea here is that, okay, what if the canary is actually not in the cache, right? This is a trigger for speculative execution. And the idea is that we might actually still be able, okay, this is a detailed view of what the compiler actually introduced. Of course, whenever you compile with the stack canary, that's the assembly code that the compiler injects transparently in your code. So if we can get this TLS section where the stack canary not into the cache, then we're going to be able to perform speculative execution and maybe get to that return with the value that we decided. And so the idea is that then from there, we can actually start a ROB chain, and we can build whatever side channel gadgets we want. Okay, before going further, I just want to give you a small demo of this working, just to make sure that you believe me until the end. So we build like a very small demo where there is an attacker, Trinity, that is trying to leak from the metrics like a secret sentence, okay? So is it readable? Somewhat. So, okay, we have like two programs, the metrics and Trinity, right? On the left-hand side here, we have Trinity. Here we have like some initial routines that we use to help the attack. Of course, in the real-world end-to-end attack that we build, we don't really have this because this is still a CL Flash operation. What we do in the Trinity program is basically just one second. Here we perform a fork, right? And in one side of the fork, then on one side of the fork, we basically start the metrics, and we just give to the metrics some malicious input, right? The metrics is holding our secret and is running on its own CPU. And by giving the certain type of input, we are triggering a buffer overflow into the metrics. And then what it does, the Trinity is basically is handling a shared array where we expect the signal of our spear attack to be found. So the shared array is built up between the Trinity and the metrics. And there, basically, we expect the signal to be shared in between the two programs. And so here, basically, we just, this particular piece of code, we just like take the time of accesses, and then we try to gather which was the byte that we recovered. Okay. Okay, just one sec. So yeah, here is where we actually exec the metrics. And in the metrics, as you can see here on the right-hand side, we have like the metrics quote, which is the generic quote we get returned, and then we have a secret quote that is the one that we want to leak with this attack. As you can see here, to perform this attack, we introduced a gadget that is doing the leakage, which is pretty much like a Spectre v1 type of attack. We didn't build the ROP chain here because it's just like more complicated to explain. But overall, it's, I will show you later like for the end-to-end attack how we did that. And here this is basically the very simple code of the metrics. If we input 1 into the metrics, we just get 1 quote. If we put 2, we don't get anything. But here, where there is the read, there is actually the buffer overflow that we are trying to exploit. As you can see, the input is a buffer of 16, but then the read is actually reading 0x40. Normally, this program, we compile this program with the stack canary. So this is not actually exploitable from the architectural point of view, so we don't get a shell, right? But we leverage the stack canary to actually leak data from the matrix. Okay. So now, just to show you that like how it works, this program. If we put 1, we just get everything that is as a beginning as an end. And if we input 2, we don't get anything. Now we trigger the metrics. The Trinity program. And what is going to happen here is that the Trinity program is launching the metrics, it's triggering the buffer overflow, and with that, we basically are able to overwrite the return value, and we send the speculative execution into the gadget that was leaking the information. As you can see, like this, the sentence is building up, but not all the characters are correct because, of course, yeah, this type of attacks can be noisy. So you need to tweak a little bit like the settings and make sure that the cache offsets that you have for the timing access is correct and so on. Of course, by tweaking it, you can get a perfect iteration, or by simply like running more times, you can you can get this, the attack, basically you can fix the symbols. And this was the secret code that we were trying to leak, okay? Which is a German sentence for who doesn't speak German. I mean, this was built by my colleague. This basically says that everything has an end, right? But only sausages has two, which, I mean, unfortunate, but. So, okay, as you could see, like this attack works, but still there in this demo, there were a few things that we left as not really, basically, there were still like some crafted situations. For instance, we put a gadget that we wanted instead of using a rope chain, and we were still using the CL flash, so we were not doing the eviction. How can we do this in the real world? So for the canary eviction, we came up with a technique to finding the eviction set where the canary is stored. And the attacker here, what it does is starts two programs, right? The first program is, so the second program is actually compiled with the stack canary. And the first program is trying to load all the eviction sets. So it's basically loading data at various points, and it's trying to load stuff into the cache, okay? The second attacker program, what it does is trying to access the stack canary location in a loop, okay? And we know that the stack canary is executed is accessed very often, because whenever we end like a specific function, the stack canary is checked, so it is accessed to be controlled if it's still there and still like the same. So it's always cached, so it's always fast to be accessed. However, if the loading of the eviction set done by the first attacker program is successful, we evict from the cache the stack canary, which means that now the access to the stack canary is going to take more time, because the CPU needs to wait for main memory. So whenever this happens, the attacker program number 2 is going to tell to the attacker program number 1, okay, you found it. This is actually the right LLC slice and cache set. And so then we can use that information later on to evict the stack canary from the victim program. Now the second attacker program is going to exec the victim program where we want to steal the information. And there is a specific thing about Linux and the exec, is that they don't, with the exec system call, the TLS segment is actually not reinitialized, which means that when we run the victim program, the stack canary is going to be in the same location of the attacker program number 2, which means that whatever we found as a eviction set is actually a valid information that now we can use to perform the attack. And so we can, like this, trigger speculative execution. And this information is what we are going to use in the eviction loop, so the stage 4 I was mentioning before, which is very important for the success of this type of attacks. So by, with the eviction loop, we can force the stack canary in the victim program now to be outside the cache. So now let's have a look a little bit at the speculative ROP that I've been talking so far. So in this work, we were the first one to actually try to achieve speculative ROP, and we did it successfully. So the gadgets we used are the following. The first gadget here is basically doing an access of a byte in memory, and is based on the victim address that we want. And this is basically just purely retrieving 1 byte. The second array access is going to do a shift of this value, because we want to index it based on the array, the side channel array that is used to share the signal. Now, one thing that I didn't mention so far is that this test array, or a side channel array, in the previous scheme, I always showed that the cells of the array are actually just purely a normal array, so each cell is its own value. But we cannot really do that in the real world, because of course there is cache prefetching. Every time we access something, the full line of cache is prefetched into the cache. So if we leave an array of 64 values, let's say, and we just leave it at that, then whenever we access the first value to test, everything else is also loaded into the cache. So we lose the signal like that. So what we do in this type of attacks is we generate an array that is much bigger, right? So let's assume we want to leak 1 byte. So we have 256 possibilities. It means that we will need to have like 256 cells array, but each one of these cells needs to be spaced out of a size that is greater than the cache line. Otherwise, we are going to lose the signal, and that's what we do here with this particular shifting operation. Then what we do, we basically need to base the index that we just compute into the array that we use to share the signal. And finally, we perform the load, which is going to bring the signal into the cache. Okay? So the final step, of course, that I haven't talked so far is the fact that once the attacker sends the payload and the victim send the signal into the test array, then we need to go from the attacker point of view and time the access of this array. You might wonder, how did you get like an array that is shared between the attacker and victim? What we did in Linux is pretty easy. You can use every shared library, right? Shared library are placed by Linux and are reused. The physical pages of the libraries are always reused in between programs. So from the attacker program, what you can do is like you can just preload a library that you know that the victim is going to use, and you just select a piece of code that is not actually called into the victim, otherwise you get some noise. And what you do is like you evict all that library code from the cache, and that becomes your test array. And so what we did here, as you can see in the bottom, we used the libp thread to perform this attack. So the code that we the code that we exploited was actually from libpng. Was a buffer overflow in libpng, and we relied on the libp thread to actually use this, gets this shared array, okay? And so by doing so, then we can get like 1 byte at the time of the secret. So the results, of course, is works, and we got like a leakage rate of 0.3 bytes per second. Of course, you need to, as all these type of attacks with side channels, you need to rerun the attack to make sure that your signal, you don't get noise in the signal, and do some statistical analysis. And we tried it on Skylake and Coffee Lake. Of course, this was just one attack that we presented in our work, which was specifically on this, like exploiting the buffer overflow, leveraging the stack canary to perform this attack. But we also looked into the other variants that I was mentioning at the very beginning of the talk. We looked, for instance, for the case of, we looked at memory safe languages, how you can exploit the checks that memory safe languages introduces. They introduce, and we looked specifically to Golang and Rust, and both of them were affected. And for Go, we reported our findings, and the developers introduced a Spectre flag, which introduced some masking whenever there is like an array handling in Go. And we also talked with the Rust developer about this. There are like more, I mean, I cannot go too much in details, of course, in this. If you are interested, we have like a blog post going very much in details on this memory safe languages part. We also looked into control flow integrity, so the corruption of forward edges, right? And we looked at the implementation of LLVM CFI and GCC VTV. We found out that LLM CFI is actually not bypassable, and this is due to some design decisions from the LLVM people, because some of the labels that are used for this integrity check, they are actually embedded in the code. So whenever we try to, of course, evict the label that is used for checking that the target is correct, we are also evicting the code that we want to execute. And this is basically automatically stops speculative execution, because if the code is not into the cache, we cannot execute it. And so basically by luck, let's say, but in a good way, LLVM CFI is not bypassable. However, GCC-VTV use a different type of checks, and that one we were able to prove that we can get a signal out of it. So yeah, what we basically take as a point from LLVM CFI is actually that these type of attacks are very implementation dependent. And so if we want to make sure that everything that we have as mitigations is Spectre safe, we will need to go and really look at how these are implemented at the low level, and to make sure that are actually they withstand also these in their threat model. And most of them were not actually developed with Spectre in mind, because were developed much earlier in time. So we will need to go and review them. So let's talk a little bit about mitigation before closing the talk. Of course, there are mitigations against spears. There are some inlining instrumentation that can be done. Of course, these type of instrumentations, they require you to modify the code. So you need to recompile the code. There are some compiler passes already available, like LLVM speculative load hardening. But the problem with these is that they all are based on heuristics, because it's very hard to decide if a piece of code is vulnerable or not. It can actually lead to some leakage. And so there is always the trade-off between getting coverage. So we can place in every load on the code this protection, this inlining protection, but this will mean that the code runs 10 times slower, 100 times slower, right? And we don't want that. So it's very hard to find the coverage, and if you don't cover enough, then you might still leave some cases in which these attacks are still possible. Some examples of this type of inlining: we have L-fencing, L-fence, M-fence, all the fencing, but these are the worst in terms of performance, and there is also branchless masking that whenever there is, like, for instance, a jump or a call, if there has been a corruption, they can basically redirect the speculative execution into like an infinite loop and so on. There are also mitigations by design. There's been like a lot of activity from the microarchitectural side of things, right? Some of these research aim to introduce new data flow that is happening in the pipeline of the CPU. So the pipeline of the CPU now is able to, with this type of work, is able to figure out if there are like some forwarding of data that is actually, it should be illegal, and they prevent it at the microarchitectural level. And this type of work will actually solve the spear problem, as well as like many other of the Spectre, in the Spectre family. There has been also some work trying to, like, aiming to change the cache design, because most of these attacks rely on the cache side channel, right, so to be performed. So they were like, okay, let's fix the cache and we are done with it. Well, this is not really like how it works, because cache side channel is one of the most used because it's the most well known and is also easy to use in a way. But there are also other side channels, and for instance, in other work that with my colleagues, we show that we can use the BTB, the branch target buffer, as a way to actually store some value that we can retrieve from a different process. So you cannot really say we solve the cache side channel and we are done with it. There is a lot more that should be done. And one of the problems with this by design, of course, even from the data flow analysis part, is that they are going to be available only on newer CPUs. And we know that CPUs tend to have like a build cycle quite long. So, and also these don't fix for all the hardware that is legacy or pre when this mitigation will be available. So we'll still need to deal with this until all the hardware that doesn't have this mitigation is gone. But we know that it's kind of utopia. So takeaways from this talk is that Spear is able to bypass mitigations and memory safety mechanism to leak confidential data. And our takeaway here is that we really need to go and try to redesign and think about all these mitigations with this new Spectre word in mind, because actually most of these are still vulnerable because of that. These type of attacks are complex, but we show that it's actually possible to pull them out end to end, right? And as everything at first, looks complex, but the more we build tools that are aiming to help with like some of these phases I described today, the better accuracy we can get, and the faster we can actually pull them off. So we see them like already now things have been like going faster, and more of this type of attacks have been discovered just because we are getting better at writing tools and we get better information to build them. And also in this talk, we showed that speculative ROP is actually possible, and it's actually making it much easier to provide the Spectre V1 gadget that was not foundable before because it was not really possible. It's not really in the code. And that we believe also, me and my colleagues, of course, that speculative execution attacks will be with us for a long while, as has been like the buffer overflow. I think we will still need to deal with them like in the next decade at least, or even more. And so we'll see more tools, more defenses and attacks related to this. I think you can. So in particular, there's been work on tooling of fencing, but not much in defense. Besides the microarchitectural stuff that I showed before. And I think like there is going to be more work also on that. To conclude, I would like to thank my co-authors on this work and my colleagues. So Anil Kurmus, which has been also, is known here in BalCCon, has been here a few times. Alexandra Sandulescu, Alessandro Sognotti, and then from my old university, Engin Kirden, Will Robertson. And with this, I conclude if you have any questions. Or
So thank you, really interesting. I was just curious, did you also run this again against the latest Intel mitigations, Contraflow Guard and the other things, CFE and the AMD equivalents?
So we did not. This work was completed before, like those were available. Actually, we still think like that these type of attacks are still possible. There are ways of like circumventing them. Yeah, but I haven't tried it practically. But on a theoretical level, we looked into it when they were coming up, and we think it is actually possible to still bypass them.
Thank you.
Anyone else? Are there any other questions? Well, that's it then. Thank you so much for the talk.
Thank you.